A tutorial on basic mixture problems. In differential equations, one of the applications of linear differential equations, first order linear differential equations, is in solving what we call mixture problems. And typically what is going on is that we have some kind of liquid flowing into a tank and at the same time flowing out of the tank. And the liquid is a mixture of, say, water and salt, a uniform mixture always kept well stirred. And we want to model a situation with a differential equation to figure out how much salt is in the tank at time t. And the way we do this is we set up a differential equation. Actually, it's an initial value problem. And we solve the initial value problem. And we state the desired conclusions. So I guess in order to, well, I don't guess, I know, in order to get started on a problem like this, we have to be able to read the problem, analyze the situation, figure out what it is that we're being given, what it is that we want to find, and set up the initial value problem. If we can't set up the initial value problem, then we can't get started. So let's focus on first figuring out how to set up the initial value problem. The way we set up the initial value problem is as follows. First, we define some variables. We'll say let A of t equal the amount of salt, number of pounds, say, in our tank at time t. Of course, our goal here will be to find a formula for A of t. And we do that by solving a differential equation that involves A of t. Now, to get the differential equation for A of t, we use the fact that the rate of change of A of t at any time t is equal to the rate at which A of t is the rate at which the salt is going into the tank minus the rate at which the salt is going out of the tank. That is actually our differential equation. This equation that says rate of change of A of t equals rate of salt in minus rate of salt out is the actual differential equation. But of course we want to express it symbolically. And we know that the rate of change of A of t at any time t is the derivative of A with respect to t, which is dA dt. So the rate of change of A of t is dA dt. So we know what one side of the differential equation looks like. Now, the rate of salt in, the rate at which the salt is coming into the tank, is equal to the flow rate in times the concentration of the liquid coming in. Now, if you look at the units on the factors in this product, this makes sense, because the flow rate coming in would be volume per unit time, and the concentration of the fluid coming in would be amount of salt per unit volume. And if you multiply those units, you get the amount of salt that is coming in per unit time. And of course, after we see this, we say, oh, well, then the rate at which the salt is going out must be the flow rate out times the concentration of the fluid that's going out. So that's how we write our differential equation. Now, to see how this really works, it probably would be best to look at a particular example. For our first example, this is problem number 21 in section 3.1 of the ZIL differential equations book. It says we have a tank and it contains 200 liters of fluid. So that means the volume of the tank at time 0 is 200 liters. And it says brine containing 1 gram of salt per liter is pumped into the tank at a rate of 4 liters per minute. So we have the liquid coming into the tank, and the flow rate in is 4 liters per minute, and the concentration in is 1 gram of salt per liter. So we have 1 gram of salt per liter coming in at a flow rate of 4 liters per minute. Now we see if we multiply those, we're going to get the rate at which the salt is coming in. It's coming in at 1 gram per minute. So that will be the rate at which the salt is coming in. Now it says at the same time, the fluid in the tank is kept well mixed and it's being pumped out at the same rate. Okay, so we've got the stuff flowing out at the same rate, 4 liters per minute. But what's the concentration of the stuff going out? Well, the concentration of the fluid coming out is the amount of salt in the tank at time t divided by the volume in the tank at time t. Now here we're using A of t to represent the number of grams of salt in the tank at time t. Okay, so let's make sure we have this right. You've got this fluid coming in at a rate of 4 liters per minute, and in each of those liters is a gram of salt. So you've got salt coming in at 4 grams per minute. I think I may have said 1 gram per minute earlier. Maybe I didn't. But anyway, it's 4 grams per minute. So you've got 4 liters coming in per minute, and each one of those liters you have a gram of salt. So 4 grams per minute of salt coming in. Okay, and then the flow rate out is the same as the flow rate in. The rate of the liquid going out is the same as the rate of the liquid coming in. That's 4 liters per minute. Now the concentration of the solution coming out is number of grams of salt. The concentration at any time t is the number of grams of salt at time t divided by volume at time t. Now, since the flow rate in is the same as the flow rate out, the volume is staying constant at 200. So actually, the concentration of the mixture coming out is the amount of salt at time t divided by 200, or A of t over 200. Okay, so our differential equation becomes rate of change of salt, that's dA dt, is equal to rate of salt coming in, which is 4 grams per minute, minus rate at which the salt is going out, which is 4 times A of t, divided by 200. And that's our differential equation. Now, of course, that can be simplified, be written as dA dt equals 4 minus A over 50. And the initial condition involved here is the amount of salt in the tank at time 0. So we need to go back and read the problem again. It said initially you have 30 grams of salt dissolved, so that means that A of 0 is 30 grams. Now this is a nice, simple, linear first-order differential equation, so it's very easy to solve. You solve it for A of t, and you've got the formula for the number of grams of salt in the tank at time t. Now in problem 22 in the ZIL book, it says to do the same problem, but assume that pure water is being pumped into the tank. Well, you write the differential equation. It's going to be rate of change of salt is equal to rate of salt coming in, which is now 0 because pure water is being pumped in at a rate of 4 liters per minute. Okay, then minus the rate at which the salt is going out, which is again the concentration, A of t over 200, times the flow rate, which is still 4 liters per minute. So simplifying, we get the differential equation, dA dt equals negative A over 50. And the initial condition is still A of 0 equals 30. And again, a nice easy linear differential equation we can solve and get A of t, the amount of salt in the tank at time t. And one thing to be careful of in these types of problems is don't confuse the volume at time t with the amount of salt at time t. They are two different things, so be careful. Now, as a third example, let's repeat this same problem, problem 21, let's say, but let's make the flow rate out, instead of being 4 liters per minute, let's say it's 5 liters per minute going out. Okay, so now the volume at time t will not always be 200 because the liquid is coming in at 4 liters per minute and going out at 5 liters per minute, and that means that we have a net rate out at 1 liter per minute. So the volume is being reduced at a rate of 1 liter per minute. So the volume at time t, instead of being 200, is 200 minus t. Again, what we've done is we've changed the flow rate out to 5 liters per minute in problem 21. Now, this is going to change the differential equation. how we arrive at the differential equation is exactly the same. We say rate of change of salt is rate at which salt is coming in, which is still 4 grams per minute. So we have 4 grams per minute coming in. And then we need to subtract the rate at which the salt is going out. Now, it's going out at a rate of 5 liters per minute. So there's the flow rate going out. Now we need to multiply that by the concentration at time t. Now the concentration at time t is the amount of salt at time t, that's A, divided by the volume at time t, which is now 200 minus t. So the differential equation becomes dA dt equals 4 minus 5A over 200 minus t. And the initial condition is still A of 0 equals 30. Again, we have a linear differential equation. It doesn't look like it'll be as easy to solve as the other two, but certainly nothing we can't handle. Now, the things to remember in these types of problems are the differential equation comes from saying the rate of change of, let's say, salt at time t is equal to the rate at which the salt is coming in minus the rate at which the salt is going out. And then, of course, your initial condition for the salt involves the amount of salt in the tank at time t equals 0. And to get the rate at which the salt is coming in, you multiply the rate at which the liquid is flowing in times the concentration of the salt in the liquid that's coming in. And to get the rate at which the salt is going out, you multiply the rate at which the liquid is going out times the concentration of the mixture that's going out. Now, this is the part that's sometimes tricky. The concentration of the mixture that's leaving the tank at time t is the amount of salt in the tank at time t divided by the volume at time t. Now, if the flow rate in and the flow rate out are different, then the volume at time t will be a function of t. If the flow rate in and the flow rate out are the same, then the volume at time t will be a constant. That's it.